Hey, everybody. So in the last video, we defined what we mean by continuity. We have this definition, a function f is continuous at a point a, if and only if the limit of the function as x approaches a is equal to the value of the function at that point. Okay, and this has a lot of implications. We talked then about extending this to continuous over an interval and including one-sided continuity from below or from above. So we have a couple more ideas to add around the idea of continuity. The first is the following theorem, sometimes called the composite function theorem. This is a handy one for us to have. If a function, if f of x is continuous at a particular value of its input, so I'll say at x equals L, and the limit as x approaches a of g of x is equal to L, then we get that the limit as x approaches a of the composition f of g of x is equal to f of the limit as x approaches a of g of x, which is equal to L. Okay. So what is this saying? Well, we compose functions, right? So when we look at the function f of g of x, right? We first input a value x into the function g. G does what g does, spits out a value that it gives to f, then f does what it does, right? So if we're taking the limit as x approaches a of f of g of x, it means we're taking values of x that are really close to whatever a is, whatever number that is, right? We know because the limit as the values of x get close to a of g of x is L. What does that tell us? It tells us that as the values of x get close to a, the values of g get really close to L, right? That's what that statement here means, right? As x gets close to a, the values of g get really close to L. So we're taking x, making it close to a, which is making g close to L. We should be looking here now. So now, what does that mean is happening? We're putting in these values really close to x, really close to a, spitting out values really close to L. Those are then being given to f. So now f is getting values really close to L. I just realized I wrote this last statement wrong. That should be f of L. Pardon me. All right, so g is spitting out values close to L. F is taking those. They're getting closer and closer and closer and closer to L. Well, we know f is continuous there, so the limit, so it's like we're taking the limit as the input values of f go to L, so that because it's continuous there, it spits out the value of the function, okay? So let's illustrate this with an example. Let's look at, we'll take f of x to be cosine of x. And we'll take g of x to be x squared minus 1. Okay. So we looked earlier in a previous video, we saw that cosine is, oh, sorry, let me write the limit I want to express. So we want to look at these functions and look at the limit as x goes to 1. That's what I'm doing. Of f of g of x. Okay, so what does that mean? That's the, actually, let's just make this mimic the definition over here. The limit as x goes to a of f of g of x. This is going to be the limit as x goes to 1 of cosine of x squared minus 1. Okay. So we saw in a previous video that cosine of 0, sorry, that cosine is continuous at 0. And we can also see that this function in here, x squared minus 1, the g function, if we take the limit as x goes to 1, is going to be 0. It's a polynomial, so we just evaluate it. So what this theorem tells us we can do is I can slip this limit inside here. Right, that's the part of our theorem that looks like this. All right, now we apply the limit laws. We know that the limit as x goes to 1 of x squared minus 1 is a 0. So we end up with cosine of 0. That's where we have f of L. And in this case, cosine of 0 is 1. And so this composite function, as it gets closer and closer and closer, as the input gets closer and closer to 1, turns out the output is also getting closer and closer to 1. Now, when I did this, I looked at the functions and thought, well, that function inside, I know that its limit is 0 because it's a pretty quick one to do in my head. It's a polynomial. And then I already knew about cosine being continuous there. In practice, you don't always have that information ahead of time, but what you do is recognize you have a composition of functions. So you go ahead and slip the limit inside. If you can take the limit of the inside function, and it turns out the value that you get is a place where the function, the outside function was continuous, you know what you did was okay. If that doesn't work out, then you say, I never should have done that, and try something different, right? Okay, so that's this composite function theorem, right? We use this a lot when we have things inside of square roots, inside of, well, like we have here, our trig functions, but we can't use them on the trig functions very often as of now, because we only know that the trig functions sine and cosine, we show that they were continuous at 0, but we can use this composite theorem function to show that they're actually continuous everywhere. So let's go ahead and do that now. It's actually pretty straightforward. So the rule I'm going to show, or at least show it partly, is that the trig functions are continuous on their domains, right? Just like our polynomials and our rational functions, right? So with sine and cosine, their domains are everything. So they're continuous everywhere. And tangent, cosine, cosecant, and cotangent are continuous on their domains. They all have asymptotes at certain values, where obviously they're not continuous there. They have infinite discontinuities. But wherever they're defined, they are continuous. So how do we show this? Well, what do we need to show? We're going to just do it for cosine, and the other ones follow pretty in a similar way. We need to show that the limit as x approaches a of the cosine of x is equal to the cosine of a, right? That's the definition of continuity at some point a. So we want this where a can be any number. So let's start there. We'll say let a be any real number. Then the limit as x goes to a of the cosine of x is equal to the limit as x goes to a of the cosine of x. And we're going to add 0 to this, so we're not changing it. So I'm going to say minus a plus a. right? So I can add a and subtract a inside cosine. I'm not changing anything. It's still equal to x, but I'm going to put parentheses here just to highlight something. We've now got cosine of two things added together, two values. X minus a is one value and a is the other value, okay? Well, there are rules. There's a sum rule for cosine. So I'm going to, all right, this cosine of this plus this can be rewritten as the cosine of x minus a, cosine of a, and then it's minus sine of x minus a sine of a. All right. Now I'm going to start using some limit laws, right? So this is just the sum rule for cosine. I'm going to use some limit laws. I've got two different expressions, this and this, two different functions that I'm taking the limit of added together. I can split that limit across each of them. Limit as x goes to a, cosine x minus a, cosine of a, minus the limit as x goes to a of sine of x minus a, sine of a. Oops, I need that last one. All right, now notice a is some real number. So cosine of a and sine of a are just constants. According to my limit laws, I can take constants out front. So let's rewrite this as cosine of a times the limit as x goes to a of cosine of x minus a minus sine of a times the limit as x goes to a sine of x minus a, right? So again, cosine of a and sine of a are just numbers, so I can pull them out, okay? Now here's where we use this composition, this composite function theorem. I can take this limit inside because notice as x goes to a, both cosine and sine, the function x minus a that we're composing with cosine and sine will go to 0, and both cosine and sine are continuous at 0. We already know that. And so just like in the above problem, I can slip this limit inside. Oops. I'm doing it here as well. We get sine of the limit as x goes to a of x minus a. All right, so now we get cosine of a. The limit of x minus, the limit as x goes to a of x minus a is just, we can plug in a, we get 0, so we get cosine of 0 minus sine of a, and we get sine of 0. Cosine of 0 is 1, so we're left with cosine of a. Sine of 0 is 0, so it doesn't matter what sine of a is because that's multiplied by 0, it disappears. And so we're left with the limit as x goes to a of cosine of x is just the cosine of a, which is enough. Now this shows that it's continuous at any real number a, so it's continuous on its whole domain. I won't go through it, but you can do a similar exercise with sine, right? Using some of the trig identities to do this kind of a manipulation. And once you have sine and cosine as continuous everywhere, the rest come from using the limit laws. For instance, if we already know that sine is continuous everywhere and we want to look at the limit as x goes to a of the tangent of x, we can simply write the limit as x goes to a of sine of x over cosine of x. But we know that this is according to as x goes to a sine of x as x goes to a cosine of x, which is simply, since these are both continuous, just sine of a over cosine of a, which is the tangent of a. So notice we have that the tangent of a is the limit is equal to the limit as x goes to a of tangent of x, which shows that it's continuous. The only part where this doesn't work is when this limit here, if this is 0, right? That happens at all the places where tangent is not defined. Whenever the limit as x goes to a of cosine of x or cosine of a, those are the same thing because we know the limit is equal to the value there because it's continuous. So we should say something like if cosine of a is not equal to 0, this is true. But that's everywhere in tangent's domain. And so it's continuous everywhere where it's defined, right? And the same thing happens for secant and cosecant and cotangent. And so we get all the trig functions now are continuous on their domains, and we do not need to prove that. We can now take that as a fact and use it. And so that's a pretty big one. We've now got polynomials, rational functions, trig functions, and now with this composite function theorem, we can take combinations of those and know about continuity because we can look and see what's happening as long as the thing that we're composing with the other one, its limit, its value at whatever point we're taking limits to is in the domain of the one it's being put inside of, we're fine. And so we get all kinds of nice combinations now that we're able to deal with. All right, and one more piece I want to throw in now is something called the intermediate value theorem. I'm just going to state it and give a little intuition around it and one example of how we might use it. Intermediate and this just says if f is continuous on the closed interval AB, so here A and B are real numbers, and Z is a real number between f of A and f of B. I'm going to put or equal to. So we don't know if f of A is bigger than f of B or which one's larger, or possibly they're the same. But it's really easy if they're the same. We'll see in just a second. We're not when we finish this theorem up. But if one's higher than the other, then Z is just somewhere in between them, right? We don't care which one's bigger than the other, but Z is going to be a value between them. Then there is a number C in this interval AB such that f of C is equal to Z. Okay, so this is really easy to understand with a picture. Let's say this is my function f. Okay, there's a little piece of it. This is going to be the point A, f of A, B, f of B. All right, let's throw some axes on here, I guess. All right, so here's our interval A to B. So on the y-axis, this is f of A. This is f of B. Z is some number in here, right? Between f of A and f of B. All this says is if Z is between the two values of f on this function, on this domain, this interval where it's continuous, then there must be some place between A and B where the function is evaluated to be equal to that value. It doesn't tell us what that number C is other than that it's between these two numbers. That's all the information we get about it. It doesn't also tell us that there's only one. We know that there is one. There could be 10, right? So let's see why this is a little bit. Let's say I have an interval AB, right? And if I know that f of A, let's make f of A higher this time, it's here, and f of B is here, right? So if I draw on the other axes, let's draw the number Z. We have to draw, for this not to be true, I would have to draw a function that starts at this point, A, f of A, and ends at this point, B, f of B, and does not pass through this line, right? This is why it's crucial that f is continuous. If f is not continuous, this is no problem. I have a function that does this, right? Now I don't have any part where it evaluates to Z. But if it's continuous, I have to go through this point at some point, right? There's just no way I can do this without getting there. And maybe I go through a whole bunch of times. There's nothing wrong with that either, right? In the case that f of A and f of B are the same, well then Z to be between them or equal to would just have to be them, and then the number C is at the endpoints. And maybe those are the only places, because maybe the function does this, or maybe again, maybe there's many places where it evaluates to that because it goes up and down, right? So that's the idea of this intermediate value theorem, right? It's an obvious maybe statement about continuity, right? We can make some pretty good real world intuitions about it. For instance, it's like, you know, I know when I was a child, at one point I was 2 feet tall, and now I'm over 6 feet tall. Well, there has to have been a point where I was 4'6", right? Because I didn't jump from one height to the next. Or if it was 1 o'clock earlier and now it's 2 o'clock, at some point it was 1:35. Right? We had to get there by passing through all those times. That's another way to think about this. And that's why you need things that are continuous. If we were able to skip ahead in time, then we could have skipped that. That would be a discontinuity. But when things are continuous, we have to pass through all the intermediate values. That's what this is telling us. And this is sometimes interesting. There's a lot of places where this can be helpful. One such place is the existence of zeros, right? It's often impossible or very difficult to find out if a function, to find the actual zeros of a function algebraically, but sometimes it's important just to know that they exist. So for example, if I have the function f of x is equal to x squared minus cosine squared of x, right? This is a difficult function to solve. Right? Algebra won't work on this. We can't get that cosine, that x out of that cosine without at the same time putting the other x inside of a inverse cosine, right? So if I want to know if this is true, this is going to be a really, really, really tricky equation to solve. However, notice that f of 0 is 0 minus cosine squared of 0. Cosine squared of 0 is just 1, so this is -1. Right? F of 0 is -1. Notice also that f of 2 is equal to 2 squared minus cosine squared of 2, right? Well, what can you say about cosine squared of 2? I don't know what the value of cosine squared of 2 is, but I do know that it's less than 1. It's between 0 and 1, right? Because cosine is always between -1 and 1. When we square it, it's going to only be between 0 and 1. So I'm taking the number 4 and subtracting some number, but that number is less than 1. So it must be the case that this is greater than 0, right? So f of 2 is greater than 0. Okay, that we can say very clearly. Well, what that means is that at 0, my function is down here, right? At -1, this is 0, -1. And at 2, it's somewhere up here. I don't know what it is, but it's some positive value. That's, we can say without hesitation. Now, because f is continuous, how do we know f is continuous? Well, notice that f, let's take the limit as x goes to a of f of x is going to be the limit as x goes to a of x squared minus cosine squared of x, which is the limit as x goes to a of x squared minus the limit as x goes to a of cosine squared of x. We now know that we can get polynomials by simply evaluating them. So this is going to be a squared. We can use the composite function twice here. We take the limit inside the squared function, then we take it inside cosine. We know both of those are continuous, and we end up with cosine squared of a, right? And so this just tells us that, or this is equal to f of a, which means that the limit as x goes to a of f of x is just equal to the value of the function there. So this function is continuous, right? And this is actually a neat little, as long as we're on the domain of both functions, when we add or subtract continuous functions, we get more continuous functions. So what that means is whatever the shape of this graph is, however I might draw it, right? It has to cross through the axis at some point, this horizontal axis, the x-axis, right? And again, I don't know, maybe it crosses through several times, or maybe it just goes through once. But however it travels this path, because it does it continuously, it has to pass through 0. Okay, let's take a look at a computer graph of this. Here is the function, right? It's an odd parabola, or it's an even function, but it's an oddly shaped. It looks almost like a parabola, which makes sense. We've got that x squared in there. Notice it does clearly have a 0 here. Oops. And in fact, it has one on the other side because it's an even function. So we can make the same argument we just made by looking at the graph passing from 0 to the value at 2. We could look at -2 in the same way because it's an even function. So let's just examine this function just a little bit. It's kind of an interesting little one. There's cosine squared, right? It's this trapped between 0 and 1. It's always waving between 0 and 1. And we're subtracting this number between 0 and 1 from a parabola, right? X squared is a parabola. So when cosine 0, we subtract nothing. It'll share those points with the parabola. And in the other places, depending on how much we're subtracting, it's a bit below the parabola. So it's almost like we're taking this wavy line. That red graph is the parabola. The purple is where the cosine squared is positive and it's being subtracted from the parabola. So we're a little bit below wherever the purple graph peels away, right? And the amount it peels away, right? If we look at the height of cosine squared, we should find that right here, we're being separated by that same amount. And where cosine squared is 0, there is no difference between the parabola and the function we have. Okay, in any event, that's the intermediate value theorem and one of the places in which we might find ourselves wanting to use it. That will do it for this one. Thanks, everybody. I will see you next time.